Hi friends, welcome to the channel Unshackling Sudokus and Puzzles. Ashish here, and today I'll be covering a classic Sudoku on our channel. Now this Sudoku is constructed by Awedish, and I really thank the author for giving me an opportunity to cover a video on our channel. I've actually tried this Sudoku earlier, and to be frank I couldn't solve this Sudoku myself. Even after taking the hint from the author, actually even after getting the hint from the author, I couldn't solve it, and then I had to look deeply into what the logic and how actually it works, and after which I could solve this Sudoku, but it took a lot of time for me. So this is really an amazing Sudoku. So I would highly recommend you to try the Sudoku yourself. Get the hint. I'll actually give you the hint. See what the hint is, and with that, if you could try to solve this Sudoku, it will really be amazing, right? So before going to the Sudoku, I would highly recommend you to please subscribe to the channel Unshackling Sudokus and Puzzles if you haven't done so. It will really motivate us to cover videos on regular basis. And if at all you have a request for any Sudoku variant or a puzzle genre, do let us know in the comment below and we'll surely make a video on it. And now coming back to this Sudoku, so classic Sudoku rules apply. You need to place digits from 1 to 9 in each row, each column, and 3 into 3 box without repetition, right? So let us try to solve this Sudoku using basic Sudoku techniques and see where we reach, right? Okay, I could see that you get 1 in one of these two cells, you get 2 in one of these two cells, you can have a 2 here and 2 here and 2 here as well. So 2 is in one of these two cells. The same thing it works for 1 as well, I think. Yep. Yes. Okay. We have a 9 here and a 9 here. So you have 9 in one of these two cells. That gives you 9 in one of these two cells, right? Okay. You cannot have a 4 here, so 4 is in one of these two cells. That gives you 4 in one of these three cells, not required for now. 3 is in one of these two cells, so nothing with the 3 here. You have an 8 here, so 8 is in one of these two cells. That gives you 8 in one of these two cells. Okay. Same way you have a 9 here actually. So that's a 8-9 pair here. That's amazing. In this box you have an 8-9 pair. So 9 is in one of these two cells. So 8, then you have a 2 here, and that's not working out. Uh, 1 and 2, it's not working here as well. So the logic that we are going to use is called set equivalence theory, right? So what is actually set and how do we use that? So before going deep into the logic, let us just see what a basic thing what a set is, right? Let me show you what a set is. I'll have two equal blocks of cells here, and both of those blocks will always have to be equal. I mean to say I will have two blocks of set. I won't have equal blocks of set. I will have two different blocks of set, and both of those sets will have to be equal. Let's see how does that work. So let me just give you an example here. Okay, let me mark that. Okay, so let us assume that I am taking box 1 and box 5. I'll mark those with green. right? So I have two sets of 1 to 9, right? I have exactly 18 digits, and they are just nothing but two sets of 1 to 9. Now what will I do is, I'll take two more sets. Let me explain you what are the two sets. I'll mark row 6 and row 3 in other color, right? So I marked two more sets of 1 to 9, which is nothing but row 1, row 3 and row 6. What I will do is, I'll delete all the cells which has both the colors. I mean to say, I'll just uncolor all the cells which are of two colors. So these cells are nothing but of both the colors, green color as well as the pink color. I'll just remove all those cells here, and if you see now, there are exactly 12, yeah, exactly 12 green cells and 12 pink color cells, right? What I have done is, first I had 18 green sets, I mean to say 18 green cells, and then 18 pink cells. So both of these were equal, because 18 green cells were two sets of 1 to 9. Exactly the same with pink cells. 18 pink cells were digits from 1 to 9, two sets of 1 to 9. Then what I did was, the common cells from both of these colors were removed, right? So let us assume that 3, 8, 6 and 1, 2, 5 were removed, 1, 3, 5 were removed from both of these pink and green cells. So whatever the remaining cells are, what are the remaining cells, the whole remaining pink cells will have to be equal to the whole remaining green cells. That is what is called set equivalence theory. You can do this with any number of any sets of 1 to 9, right? So if I take 1 to 9, three sets of 1 to 9 with one color and three sets of 1 to 9 with other color, and just remove the mutual or the common cells of both of those colors, so the remaining cells, the remaining color that are still marked will always have to be equal. Or sometimes you can have that the remaining set is sometimes one greater than. So let me give you one more example here. Is, let us assume I had one more set of 1 to 9 as pink cells. So in this case, the theory would be, one set of 1 to 9 is always greater than the set of green cells, in pink cells, I am sorry. One set of 1 to 9 in pink cell is always greater than the number of cells in green. So example, if you had in this case you have 21 cells, right? So in these 21 cells, exactly 12 cells of pink is equal to 12 cells of green, and one set of 1 to 9 is extra. It just works this way. Now how do we use that in our this Sudoku? So I hope you got what is set equivalence theory. You just take two sets of, or any number of sets of one color equal to those number of sets of different color, and then the common cells between both the colors will be ruled out, and then the remaining cells will always be equal, right? Will always be equal, because you actually remove the common cells from both of the sets, and that means that the remaining cells will always have to be equal, right? And now using that theory, let's see if we are able to solve this Sudoku. Even after, so this is called set equivalence theory. I have solved Sudoku or two using this theory, but even after getting the logic that a set is used in this Sudoku, I couldn't find which set of 1 to 9s will have to be used. I actually couldn't find that. It was really difficult but really amazing. Now let us see how do we use set in this Sudoku. I mark row 1, row 5 and row 9, column 1, column 5 and column 9, right? I mark that with the green color. So I have 6 sets of 1 to 9, but in this case these cells are used twice. Now of course, if there are 6 sets of 1 to 9, right, you will have exactly 54 cells used. Let us see if we have 54 cells used or not. You have these 9, 9 and 9, right? 27 plus you have 6, 33, plus 6 is 39, plus 6 is 45. So of course there are only 45 cells and it has to be 54 cells, But if you see here, we have used these 9 cells twice. So for this row I have used these 3 cells, but for this column also I have used this cell. So this cell is used twice. Same way for this column I have used this cell twice, and for this column I have used this cell twice, right? So 45 plus set of these 9 cells will give you always 54, right? So I have used 54 green cells for now. Now the other set of color, the other color would have to be box 2, box 3 and box 6, right? Box 4, box 7 and box 8, right? Again these are nothing but 54 cells. Let me mark that with the red color here. Now what was our logic before? All the mutual cells, all the common cells or all the cells having two colors in common will have to be ruled out, right? I'll rule out all of these cells because they are common in nature, right? They have both the colors available. So I'll remove that, but make sure that these cells were used twice. So now we'll at least use it once, right? One of the usage is already ruled out using the red color, but the other usage is still there. Now if you count the number of cells in the green area and the number of cells in the red area will always have to be equal. Let us count that here. You have 8 plus 8 is 16, plus 4 is 20 and plus 4 is 24. You have exactly 24 red cells, which means you will always have exactly 24 green cells including the pink ones, right? Let us count that here. You have 5 plus 5 10 plus 5 is 15, 16, 17, 18, 19, 20 and 21. Of course you have only 21 cells here, but you have 24 cells in the red, so you have 3 more cells in the green color, which is nothing but these cells are used twice, right? These cells are used twice. So 21 plus ones each of 9, 8 and 7 gives you 24. So which means these 24 cells will always have to be equal to these 24 cells. Now if you see here, all of the green cells are given with 9, 8, 6 and 7, but all of the red cells are given with 1, 2, 3 and 4. Now let us count how many 1, 2, 3 and 4s we have in the red cells. 1, 2, 3, 4, 5, 6, 7, 8, 9, 9 and 10. You have 10 digits with 1, 2, 3 and 4 in red area. Those 10 digits will surely be into the green area as well. But how many green area we are remaining with? We have unused area in greens. 1, 2, 3, 4, 5, 6, 7 and 8. And if you see here, 1 and 2 is already given here 9 and 10. Which means all of these green 9 or 10 areas that we have, actually 8 areas including these two ones which are used, will have to be 1, 2, 3 and 4. Amazing guys, because the set of green cells will always be equal to the set of red cells. These 10 green cells will always be equal to the 1, 2, 3, 4 that we have in the red cells, and the vice versa. All of the red cells that we have not used now will always have to be 6, 7, 8, 9, and the number of 6, number of 7, number of 8, number of 9 are already given here. So which means in these red areas you will have 1, 9, 2, 9, 3, 9, and this is used twice. You will have 4 9s in this red area, 1, 2, 3 and 4. 4 8s in this red area, 3 6s and 2 7s in this red area. So which means we can directly mark that these cells would have to be 6, 7, 8 and 9. 6, 7, 8 and 9. And these cells would have to be 1, 2, 3 and 4. There cannot be any other cells. Amazing, right? So if you see here, using this logic, the sets of the numbers used in the red area is equal to the numbers used in the green area, according to the logic that we have used, that is called set equivalence theory. Amazing. Try to solve this without the set and you will actually get stuck. It is really a difficult one. Now let us remove the candidates from the cells. See, because this can never be a 4, right? This is not a 1 and 2 and a 1 and 2, so you got a 3 4 pair directly here, right? This 8 will remove 8 from these 3 cells, right? And this 8 and 9 will remove 9 from this cell. This 9 is removed from this cell, so you have a 6 7 pair in this row. This has to be a 9, sorry, this one. So 9 is removed from here, 7 is removed from here, right? 6 is removed from both of these cells, these 3 cells. 6 is removed from these 2 cells as well. 8 is removed from here, 9 is removed from both of these cells. Okay, you know that 9 has to be in one of these 2 cells, so this cell cannot be a 9. You have a 7 8 pair here, so this cell is a 9 here. A 9 is removed from this cell. Okay, you have a 9 in one of these 3 cell, cannot have 9 anywhere here, so this cell is a 9 here. You cannot have 2 and 4 here. You cannot have 1 and 3 here. You cannot have a 3 here and a 4 here and a 3 here, right? We have used all the possible, we have eliminated all the possible candidates from each and every red and the green cells, right? It's just about solving the Sudoku now. Let us see if we are able to solve it still. This cell cannot be a 9 though. So you have to keep in mind that the whole red area will have 4 9s, 4 8s, 3 6s and 1 7, 2 7s. And same way all the green cells will have 2 4s, 3 2s, 3 1s and 2 3s. Yeah, 10. Yeah, exactly. So if you can get something using that, you can go ahead and try to solve using that, or let us see if we are missing any basic knowledge of classic Sudoku here. And okay, here the next logic that I used in the Sudoku was so even after finding all of these pairs and triplets, so we have got a pair here in this row, a pair here in this row, a triplet here in this row. So let's see if we are able to get something out of it. 9 2 2 is in one of these 2 cells. Okay, okay, so the next logic that I used in the Sudoku was a XYZ wing, actually WXYZ wing, if I'm not wrong. I'm not sure. Yeah, I think so, WXYZ wing. If you see these 3 cells, right, these 3 cells uses a extension of Y wing, that is extension of XY wing, that is XYZ wing, right? So if you see here, what happens if you have a 7 here? The moment you have a 7 here, this cell becomes a 6, this cell becomes an 8, and you can have nothing here. 6 7 6 and 8, all of these 3 cells are used and you can have nothing here. So this cell can never be a 7. This cell can never be a 7 because of the 7 8 pair. This cell can never be a 7 because of the 7 here. This cell would have to be a 7 in this row. Just with the logic that we have used, SCT, set equivalence theory, and one of the WXYZ wing, we directly get a digit here, and that digit actually solves this Sudoku. This is 6, this is 7, this is 8, this 7 and 8 gives you a 6 here, right? This 7, I remove 7 from this cell. Okay, and we get a 7 here. 7, okay, 7 is in one of these 2 cells, so that removes 7 from this cell. 8 and 9 pair, so this gives you a 7, that gives you a 6 and an 8 here, that gives you an 8 here. This 8 gives you a 9 here and an 8 here, right? Amazing. 6 and 8, so this cell is a 7 here, and that gives you a 7 here. I'm sure this Sudoku is solvable now, but let us see if we get stuck anywhere. 6, 5 and 9 here, 5, 6 and 9. This is nothing but 3 and 4 only, I'm sorry. Okay, 6 cannot be here, so 6 is in one of these two cells. So this is nothing but 1, 3 and 5, right? 1, 3 and 5. 1, 3, 4 and 5. So this is 1, 3, 4 and 5. 3, 4, 5. This cell is a 7. Again, these cells would have to be 3, 4, 5. This cell cannot be a 4. This cell cannot be a 4. So you get a 4 here. Because of the 3, 5 pair, you get a 4 here. That gives you a 3 and a 4 here. Removes 3 from these cells. So you have 3 in one of these two cells. This cannot be a 4 here. This cell cannot be a 3 here. So you get a 4, 5 pair. This cell would have to be a 3. That removes 3 from this cell. A 4 from this cell. So you have 1, 2 pair here. You need to have a 6 here. 3, 4 and 5 again. This 3 gives you a 3 here. This 4 gives you a 5 and a 4 here. That gives you 3 and a 5 here. 9. Okay. Okay, yeah. So 1, 2. This cell. Okay, 3 can be. Okay, this cell would have to be a 3. In that row. So this is 1, 2 pair here. Oh, so I think so that is correct. Let us see here. If you are doing any mistake, we will get to know that. This is 1, 2, and that is 4 and 5. 4, 5 and 6. Okay. 2, 4 and 5. So 4. This is nothing but 2, 5 pair here. So these two digits are 3 and 8. You have a 3 here. So this would have to be 8. This is 3. That gives you 1 here. That gives you 1 here and a 5 here. That gives you 3 here. That gives you a 4 and a 5 here. That 4 gives you a 5 here, right? So that one gives you a 2 and a 4 here. 1, 2, 2, 1, 5, 6 and 4, 5 and 6, right? That gives you 2, 5 and 2, 5 and 4 and 1. Okay, we have done something wrong here. No, not wrong. 9 and 8. Wow, we have solved this Sudoku. Amazing Sudoku, guys. Amazing Sudoku. The moment I saw how this Sudoku works, I was really amazed and really fascinating Sudoku. Thanks a lot, Awedish, for such a wonderful Sudoku. I have never seen a better, better and a really difficult set theory before in a classic Sudoku, and this is really an amazing one. So actually we get to learn something new with every Sudoku that we solve, right? Every classic Sudoku or every Sudoku variant that we solve, we get to learn something new, and it's all because of these authors that help us to gain knowledge of how to go on solve these new Sudokus way. I mean to say new tricks using in this classic Sudoku, right? So really thank the author. This Sudoku couldn't have been better better in a set, I would say. So I hope you enjoyed this Sudoku. I hope you actually got how a set works, set equivalence theory. And if at all you have any doubt about set theory, you can let us know in the comment below. We will surely try to resolve the doubt that you have. And I hope you enjoyed this video. Do like and comment if you want us to solve any other Sudoku variant or a puzzle genre, and please don't forget to subscribe to the channel. Thank you.